Kitab ladder, and these were collaborated with the Tapan Misra from Niger, Bhubaneswar, and Lavan from Poland, and Sunil Kumar Misra is my supervisor. And in this hybrid kitab ladder, you use the kitab chain. And motivation of this hybrid kitab ladder, as we know, in kitab chain there are only minor zero mode quasi particle existing in the edge of the kitab chain, but in long range kitab chain there are no minor zero modes, and there are a massive Dirac mode are presenting at the edge in compared to minor zero mode in case of long range. And we take both kitab chain, long range and nearest neighbor kitab chain, both include in the single kitab chain, and that makes a ladder system. And why motivation of this work is the study the topological system and how topological phase varies, including the hybridization between nearest neighbor interacting kitab chain and long range kitab chain thing here. And in objective of this model, we study the energy spectra, dispersion relation, and the phase diagram, and we confirm the topological region and trivial region. This is the basic realization of kitab chain experimental realization. As we know, the kitab chain is the basic semiconductor superconductor head-to-head structure to realize experimentally. And figure second just confirm plot the differential conductance versus a volt magnetic field, and we get at zero magnetic field we get a peak. They confirm about the minor zero mode are presenting. And second is the plot the basic. Just recall the energy topological phase of the kitab chain and long range kitab chain. In this left one figure, we plot the energy spectrum for kitab chain. In this spectrum, we show the topological region from -1 to 1 is topological region, and beyond the topological region -1 and plus -1 to 1, and this is a trivial region with no edge mode are presenting. And in long range energy spectrum in figure B, just topological region below the mu less than 1, and beyond the 1 is the trivial region with the no edge mode, and below 1 the in long range kitab chain there are massive Dirac mode and finite energy state are presenting, but in kitab chain there is a zero energy state present in the topological region. Next we discuss the hybrid kitab ladder. In this kitab ladder we just we take the two kitab chain. One is the nearest neighbor interacting kitab chain in the upper leg, and lower leg hosts a long range kitab chain, and we just take a coupling vertically. This is the interchain coupling through the T nu strength is there, and we study the how to topological phase affected by the this ladder system. And this is the hybrid ladder system, obviously not a normal ladder. In normal ladder they take the only nearest neighbor interacting in the both leg of the kitab chain. Next we plot the energy spectrum of hybrid kitab ladder with the two different strength of interleg coupling strength. Figure A corresponding to 0.5 and figure B corresponding to 1 interleg coupling strength, and figure C just zooming off the figure A and B resultant physics is there. And in figure C we just show the just different from the kitab chain and long range kitab chain is there. In kitab chain there we know the topological region only minor zero mode show the quasi particle, but in long range kitab chain in their topological region only massive Dirac mode show the quasi particle. But in hybrid kitab ladder we show the -1 to 0.75 is the presenting both quasi particle minor zero mode and massive Dirac mode is there. And second topological region we show the only massive Dirac mode quasi particle are presenting here, and beyond the this one region is the trivial region. And one interesting thing in this hybrid ladder, we see the two topological region. One is the minor zero mode massive Dirac mode, and second is the massive Dirac mode. And left one transition point mu equals to -1 is the not changing, applying just increase the strength of the interleg coupling strength is there. Third one is the just generalization of long range hybrid kitab ladder. We take the long range interaction in both leg, and just we see the transition point mu equals to 1 are splitting and generating 4 massive Dirac mode region and 2 massive Dirac mode region, and trivial region is there. And just it's again generalization of nearest neighbor or long range hybrid kitab ladder. That's why we not get a minor zero mode, because it's a long range thing is there. Third plot is the corresponding to nearest neighbor interacting thing, and in this the spectrum we show the easily the mu equals to 1 and -1 both topological region are splitting, and here generated 3 topological region. One is the 4 minor zero mode, second is the 2 minor zero mode, and left and right side of the thing. But in hybrid kitab ladder we don't split topological region in symmetrically in left part and right part is this thing. And next we discuss the momentum space and dispersion relation, and just confirm the topological region. So in this hybrid tabulator, in hybrid tabulator we just show the figure last see. Here the three topological point. One is the mu equals to -1, second is mu 0.5, and third is the 1.25. And in dispersion relation we plot for this topological transition point, and we get a gapless dispersion, and thus confirm that this is the transition point. And third is a plot the inner phase diagram corresponding to chemical potential and interlake coupling strength. We just vary the interlake coupling strength 0 to 3 strength is there. Just we see the first plot corresponding to only show the minor zero mode emissive dark mode with some finite energy state. Second is the their plot, logarithmic plot is there, and in logarithmic plot we just clearly visualize the transition point mu equals to -1 are not changed if increase the strength of interlake coupling, interchain coupling strength, but mu equals to 1 is the linearly increase and decrease. And we saw that this is dark region corresponding to minor zero mode and massive dark mode common region is there, and mid one is the bright region corresponding to massive dark mode, and beyond the -1 and dark one line is the trivial region corresponding to no edge modes. And this one this topological phase diagram again make to corresponding to long range exponent versus chemical potential. In long range exponent we increase the alpha greater than 1, then long range keteption recovered to normal keteption is there. And in hybrid tabulator we just show the topological region corresponding to mu equals to -1 to 1.25, 1.5, because this is interchain coupling strength is 1. That's why it's the asymmetric topological region generated in the hybrid tabulator with alpha less than 1, and alpha go beyond the 1 is the normal tabulator, and thus their topological region are symmetric about the chemical potential. And figure A corresponding schematic diagram, and figure C corresponding to their how total number of modes present in different topological region. In topological region first they are corresponding to 2 minor zero mode, 2 massive dark mode, in normal tabulator they are corresponding to 4 minor zero modes is there. In normal long range tabulator is there are 4 massive dark modes present, and region 2 is the only massive dark mode minor zero mode are presenting there, and trivial region is with no minor bound state here. And this is the summary of my work, and hybrid tabulator here the both type of pairing, and both type of pairing study in single platform, and we reveal all study of the phase transition, and they are significant use in the just like we know it single as platform for topological qubit candidates in this thing.
Thank you. Questions, comments? Thanks for the talk. Like in the model that you consider, the second leg has the long range coupling.
Yes.
So what effect does the strength of the runs plays in the results that?
This effect is generating on this one. In phase diagram there we change the topological region mu equals to 1, -1 is the all time reversed. That's why due to long range thing. If we take the normal type of tabulator, then it's a topological region -1 and 1 is the no integer.
What do the colors represent?
This is just a color energy eigenvalue representation. Yes, no gap just.
Okay,
Yes.
let's thank.
First of all, thanks to the organizer for this opportunity. I am Subhrajyoti, currently pursuing my PhD in IIT Delhi. Today, I am going to present some of our recent work on charge density wave behavior in copper telluride single crystal system. And we have done this study using the scanning tunneling microscopy and spectroscopy. This will be the outline of this presentation. So first I will try to give some introduction to the CDW, and then why we have chosen the copper telluride system, and then I will try to give some direct evidence of the CDW on the system and some more interesting phenomena we are seeing on the surface that I will try to explain. Now, at the beginning, so introduction part, I think few speakers already had spoken about this Peierls transition. So what happens here, like when there is a 1D metal coupled to a underlying lattice, it's not a stable system under low temperature. So what happens, like the charge becomes accumulated, and it accompanied a lattice distortion. As the lattice gets distorted, it becomes some dimer, and the Brillouin zone gets shrinked. As the Brillouin zone gets shrinked, there are some gap opening happens, and the metal becomes insulator or maybe semiconductor or semi-metal. So this can be easily explainable with the Fermi surface nesting, as Ernst Peierls did in 1955. But for higher dimensional material like quasi one-dimensional and two-dimensional case, as the Fermi surface nesting it's not perfect like 1D system. Like in quasi 1D, it's some part of is nested, and for 2D case there is not at all nesting is there. So it's really hard to explain in that case that why the charge density wave is appearing on the system. So I mean there are other factors come like electron phonon coupling and other things. Now why we have chosen this copper telluride system, because it has some hexagonal Newtonian structure, and it has from the transport data what we found, like what is reported, that this has two first order transition. One is at 314 Kelvin and second one is at 155 Kelvin, where the first order metal to semiconductor transition has been reported. Now, why this transition is happening in that quest, some group has done some STM work before. So there they have found some 2x2 commensurate CDW state on the system, but above the transition temperature there are no signature of this CDW there. So they try to relate this thing with the help of this low temperature Raman peak, so which is appearing just below the transition temperature, and that's how they try to try to relate this thing. Now, and this is due to the soft phonon mode, that's their claim. But after that, some other people have studied this system using the scanning tunneling microscopy at liquid helium temperature. There they are getting some some type of reconstruction on the surface, like 2x2 commensurate and then √3x√3, and here there are some two three different types of reconstruction were there on the surface. But the problem was, like I mean there is no gap opening there they could measure on the system. So it was concluded by them this is not due to the CDW, but due to the motion of the copper atoms on the sample surface that gives those reconstruction. But so this is very confusing. I mean, we thought like why don't we give a try that why this reconstruction was happening on the surface. So also there are some discrepancy, like we don't have enough spectroscopic data for this sample. So we give it a try, and this is our result. We have used the scanning tunneling microscopy for this, and this crystal has a hexagonal structure, as I told, and this tellurium is a van der Waal. There is a van der Waal interaction is happening. So when you clip the sample, so you are getting a tellurium layer at the top for the STM measurement. So for the for checking the quality of the crystal, we did XRD measurement. There we are getting the 00L planes, and then from the transport measurement we have verified it indeed has some first order transition at 155 Kelvin. Now to do the STM measurement, we clipped the sample under ultra high vacuum, and that exposes the tellurium layer, and that's how that the layers looks like. So this is upper layer, and there is a second layer in the bottom. So we have done all the measurement at 77 K, like liquid nitrogen temperature. There we are getting this the c-axis distance of the crystal coming around 0.8 nanometer. Now if we zoom in onto the terrace, we are getting this beautiful atomic arrangement on the surface. So this is a tellurium terminated surface. So each each of these dots are the tellurium atoms. And you can, if you zoom in further, this is the momentum space of this image, and there the hexagonal structure you can clearly see from this picture, and also some other spot like 2x2 reconstruction you can also see. So there we found out it has some 3q CDW phase, and that's a really interesting finding. Now if we go to another part of the crystal, so there we are getting like some triangular structure on the surface. But after careful analysis, we found that this is forming some star-like pattern. So then, when we did when we try to measure the distance between the stars, we are getting it is just like √13 times of the lattice constant. So that is also it making some angle of 28 degree with the lattice direction. And this is well-known Star of David pattern, and already some reported data was there. So this is monolayer 1T NBAC2, although it's a different system, but this type of star pattern they have also seen. So that directly, so we can say like this is a direct evidence of the CDW because of the Star of David pattern. Now we found out that in one surface we are getting some domains that contains the Star of David as well as some 2x2 reconstruction. So this part is there are some star, there are some triangles, and also this part is 2x2, and they are coexisting on the sample surface. Now from the K-space image, we found out those spots corresponding to the 2x2 and the Star of David. So these peaks are correspond to the Bragg peaks, and then these are the 2x2 peaks, and these peaks are corresponds to the Star of David peaks. Now from the spectroscopy, that we found like it has some type of gap opening happening around the Fermi level here, but it looks like some double gap like feature, like the outer one, this is almost around almost around 1.5 electron volt, and inner one this is 670 milli electron volt. 1.5 is too high for to be a gap, but I mean we are getting this is coming from the sample. It's not any artifacts or anything. So then these two gaps we are getting there. From the large gap size, we are trying to understand it from the electron phonon point of view that this may be due to the high electron phonon coupling, and also like some in the occupied side we are getting some peak, deep, and hump like feature, that is a some signature of the BCS superconductor. Now if you so some recent recent work people have shown like there is some specific change at this 2 transition temperature for this sample, and there they are trying to explain it from the electron phonon point of view, and that's so this is the take home message from this presentation. Like we are getting the two types of CDW on the surface, 2x2 and √13 √13. Then there is a gap opening, so they are also coexisting on the surface, and the more than electron phonon coupling thing are happening on the sample surface, because Star of David itself a complex construction on the surface. So these are the collaborators in this project, and these are our group, and thank you.
Thank you. I should ask them also ranking.
Yeah. Okay. Thank you.
Good afternoon, everyone. First, I thank the organizer for giving me the opportunity to present our work here. Today, I will be presenting one of our recent work on ultramagnetism, focusing different ultramagnetic phases and corresponding phase transition. So, let me begin with a very brief outline of my presentation. First, I will introduce different types of magnetic orders, which provide necessary background for which provide the necessary background for observing or realizing the all different types of alternating order. Then I move to model of our model system and Hamiltonian. After that, based on a self-consistent order parameter calculation, the emergence of alternating phases and corresponding phase transition will be discussed. And then I will discuss the spectral function distribution over different types of altermagnetic phases, and also I will uncover the effect of spin orbit interaction in altermagnetic phases, and followed by a conclusion. So traditionally, magnetic order are classified into two types. First one is the well-known ferromagnetism, where it gives always give a non-zero magnetization due to the parallel alignment of the spin, and corresponding energies band is showing always a splitting into up and down bands. But if we move to the antiferromagnet case, due to the anti-parallel alignment of the spin, the net magnetization is always 0, and at the same time the corresponding energy band diagram shows a degenerate overlapping in the momentum pace. Now, beyond this type of traditional magnetic order, recently a new magnetic order is discovered, that is called the D-wave magnetization. So, in this case, here also the net magnetization is 0 due to the anti-parallel alignment of the spin. At the same time, it shows a spin splitting over the momentum space. So, it's basically but this spin splitting is completely different from the ferromagnetic case. So, this spin actually alternate over the momentum part, and due to this alternating behavior of the energy band over the momentum path, it's also called the altermagnetism. So, it's basically combine the both advantage from the ferromagnet and the antiferromagnet. From the ferromagnet is like ferromagnet is show the spin splitting over the momentum part. At the same time, for the like the antiferromagnet is show the net zero magnetization. So, due to this, it's always these antiferromagnet basically are used to a very promising application in the spintonic devices. So, now here is the motivation for my present work. Already these types of altermagnetic orders is realized in the ultra cold atomic system. Now, the question that we can ask, how to get the altermagnetic order in a single orbital decorated lattice model, and how this spin orbit coupling affect the different types of altermagnetic phases, as well as how the additional introduction of additional hopping within the lattice affect the altermagnetic phases. So, based on our Lieb-5 Hubbard lattice model, I will give the all answer of this question. So, this is a well known Lieb-5 lattice model. Note that this lattice model is invariant under the two simultaneous symmetry operation. One is the time reversal symmetry, another is the C4 rotational symmetry. So, this basically indicate a primary indication of the to observing altermagnetic phases. And here we consider three types of sublattices, alpha, beta and gamma. Among these, alpha and beta are the magnetic sublattices and gamma is the non-magnetic sublattice. And here we consider the simple Hubbard Hamiltonian, here we consider the repulsive Hubbard model, and this hopping integral it can take T1, T2 or TD. T1 is basically intercell hopping, T2 is the intercell hopping and TD is the diagonal hopping. And here we defined the altermagnetic order parameter that basically proportional to the staggered magnetization, and based on this I will discuss the different types of altermagnetic phases. Not only the theoretical point of view, this Lieb-5 lattice model already realized in the experiment using some chemical compounds as well as in the field of photonics. So, first this is the energy band diagram when no Hubbard interaction is considered. So, this is basically for the u equal to 0. So, at this case it is observed that corresponding altermagnetic order parameter turns out as 0, and all energy bands coming from up and down spin, they are basically overlapped each other, and they are overlapped basically around the Fermi level. So, this basically indicate a normal metallic phase. So first one is when we not consider the diagonal hopping, and second one is when we consider diagonal hopping. Now if we tune u from the 0, what's happened? So if we tune the Haber state from 0, it is observed that after a particular value of the u, this is basically the threshold value of the u, the energies band is splitted around the momentum path, and is also follow the alternating nature around the reverse momentum path. So and there is another thing, these two bands basically separated from each other, whereas a pair of band always stay at the Fermi level. So we term this as altermagnetic isolated band metallic phase in absence of diagonal hopping when Td is equal to 0. Now what happen if we introduce the diagonal hopping in the lattice model? This basically result is now more interesting. Now if we consider the diagonal hopping, it is observed that there are two types of altermagnetic phases now can appear. So for the higher u value, this AM-IM phase is remain there, but for the lower u values, there is another type of altermagnetic phase where maximum band are overlapped around the Fermi level. We term this as a altermagnetic metallic phase. So the main advantage of introducing the diagonal hopping is this system. Basically, there's two advantage. One is reduce the threshold value of the u. At the same time, is contain a new types of altermagnetic order. This is altermagnetic metallic phase. And this is the corresponding phase diagram when Td is equal to 0. So and this T2 is the intercell hopping. So it is observed that this value of u at the transition point is basically increases if we increase the intercell hopping integral strength. So there is a clear indication of the normal metallic to AM-IM altermagnetic phase when no diagonal hopping is considered. Now if we introduce the diagonal hopping, so it is observed that now a new phase appeared in between the normal metallic and altermagnetic isolated band metallic phase, and at the same time is reduced the threshold u value. So now the phase transition is from normal metallic phase to AM-IM phase via a AM-IM phase. So now one question can appear, how can we get this altermagnetic metallic phase over a broader region over u? So here this is the answer. Here this is the density plot of the diagonal hopping as a function of u. So it is observed that this is for the lower intercell hopping value and this is for the higher intercell hopping value. So if we want to get a stable metallic phase over a broad region of u, we have to choose a lower intercell hopping strength. So now here is the spectral function distribution of the different types of altermagnetic phases. First one is for the altermagnetic metallic phases, second one is for the altermagnetic isolated band metallic phases. So here also this delta is basically mean the difference between up and down spectral function. So here also it's showing alternating sign changes over the momentum phase, which this is the plot of basically Fermi surface. So which indicate again confirm the altermagnetic phase again, and it is also follow the C4 symmetry as I have discussed in the lattice model. The lattice also follow the time reversal as well as C4 symmetry. Now we compute this total fractal function and difference in fractal function in over the momentum path. So first one is basically indicate the energy value which energy eigenvalues over the momentum path. At the same time is the difference is basically indicate the spin polarization along the momentum path. Note that these types of diagram or is experimentally realized using some high resolution angle resolve photoemission spectroscopy in the experimental work. So now another thing that we have discussed, I am going to discuss the robustness of these altermagnetic phases against the intrinsic spin orbit. Okay, just one. Intrinsic spin orbit interaction. So basically it's spin this altermagnetic phase, all these types of altermagnetic phases are remain preserved in presence of SOC. So it's these indicate a potential application in the spintonic devices due to this robustness. So this is my summary and conclusion, and this is our paper, based recent paper, and here is my acknowledgement. Thank you everyone.
Very quick question. Yeah.
Is the threshold value of the parameter?
Okay. Actually, it's depend on how you choose the intercell hopping strength. If this is the threshold value for 0.1 and so on. So if we take T2 is 0.1, this is intercell hopping, then you still use threshold is around 1. Okay. So beyond this is alternating phases, and beyond this is normal phases, and T2 is basically this one, intercell hopping. How to know?
So let's thanks all.
Yeah, so I'm Projal, and I'm going to talk about this quantum phase transition between quantum spin glass and quantum dimer paramagnet phase in a coupled Sajde-VA model. So this is in collaboration with Darshan Joshi at TIFR Hyderabad. So the broader motivation of our work is actually to find the robustness of the quantum spin glass phase. And there has been several studies about how a quantum spin glass phase melts into paramagnet phase following a thermal phase transition. But in this case, we are taking a 0 temperature limit, and we will look into the quantum spin glass phase, how it melts in quantum dimer paramagnet phase. So as a model for this quantum spin glass phase, we take into account of this Sajde-VA model, which actually gives you a spin glass phase at the ground state. So this is a Heisenberg spin model where all the spins, so interaction is all to all. So each spin is interacting with any other spin in the system, and the interaction, this exchange interaction is random in nature. So basically, if I take an average, it goes to 0, but it has a non-zero variance. Okay. So this model is very famous because of the analytical solvability for SU-M spin in the large M limit, and it has been shown that, okay, for SU2 case, the ground state is a quantum spin glass phase at t is equal to 0. And this order parameter is known as the Edwards-Anderson order, which is the long time limit of the local susceptibility that is defined in this way. So it's a spin-spin correlation type of thing. Okay. So to have a quantum dimer phase, we couple two such SOI model, Sajde-VA model. So this is one layer. Within this, every spin is interacting with every other spin randomly. And so this is like one spin from this layer 1 would actually interact with another spin of this layer 2 via some antiferromagnetic coupling. So this J perpendicular is positive in nature. So as you can see, for a simple, when in this limit, when this random interaction is very large, then it should show some sort of a quantum spin glass phase. So spins are frozen in time at some random direction. So if you take an expectation value, it is non-zero, and overall it should be 0. In the other limit, when there is no, let's say, this random interaction and there are only antiferromagnetic type of interaction, it forms singlets between two layers. So that's a dimer phase. Okay. So a rough phase diagram of this model that we can expect is that this quantum dimer phase would appear when this interaction, the ratio of this, so this is the variance, that is J. When this ratio is smaller, the quantum dimer phase would appear, and it's a gapped phase. So the energy gap between the ground state and the lowest excitation state, that is the gap, that is non-zero, and in quantum spin glass phase, it's gapless. And also, in terms of this order parameter, it's a disordered phase. So obviously the order parameter is 0, and then in QSG phase, this starts to develop. Okay. So what we do, we do an exact diagonalization of this Hamiltonian. to probe first the gap of the system. And we do it for different system sizes. For example, if I have 6 spins in each layer, up to 10 spins in each layer, and you can see that in the dimer phase, this gap is actually 1. So this gap means the singlet versus triplet energy gap. If we increase the J value, the triplon starts to hop. So basically the kinetic energy would actually reduce the energy, and this energy reduces. And in thermodynamics, so you can see there's a strong finite size effect, and one can eliminate that using a finite size scaling. And this black curve, if you see, at around 0.55, this goes to 0. So basically we get a phase transition between a gapped quantum dimer paramagnet from the gapless quantum spinless phase. Okay. One can also define a local magnetization, which is actually 0 in the quantum dimer phase and in non-zero in the spin glass phase, and beyond some certain value of 0.55, it starts to develop. So here lies the quantum dimer phase and here lies the QSG phase, and they are actually roughly telling you the same story. This J by J perpendicular, the critical point should be somewhere near this 0.55. Okay. Okay, we did a critical exponent scaling. So this energy gap roughly scales, has a critical exponent 1, and the M local, the local magnetization follows a critical exponent roughly 1.25. Okay, so but the order parameter, this Edwards-Anderson order, this can only be found out from the local susceptibility in the long time limit, and this susceptibility is defined as this quantity, which I also shown you previously. But we can take a Fourier transform to go to the frequency space. Now, the imaginary part of that susceptibility actually gives the Edward-Anderson order. It is a zero frequency contribution in that. So a typical this imaginary part is shown here. So this is the dimer phase. You can see that at omega is equal to 1, there is a sharp peak. This is the energy gap corresponds to the singlet triplet transition. And if I increase the J value, the random interaction, up to some beyond the critical value, 0.55 that we have found out earlier, you can see there is a sharp peak at omega is equal to 0, followed by a hump and then some regular part. So this hump also goes to 0 in thermodynamic limit, and we can extract the Q value corresponding to that. And yeah, so I'm showing some sample size, Q value for some different samples, and eliminating this thermodynamic, going to the thermodynamic limit, you can see this Q value roughly follows this graph, and it's also beyond 0.55, it starts to develop. So everything checks out. Okay. So one can also see from the spin glass susceptibility, this is the expression of the spin glass susceptibility. You can see that if this denominator goes to 0, then there is a instability towards the spin glass phase. So we track that quantity, and doing a thermodynamic scaling, we find out that at around 0.61 roughly, there is an instability towards the spin glass phase. And yeah, so in summary, what we did to track the quantum critical point between the quantum dimer phase and the spin glass phase using exact diagonalization. And we identified via the analysis of energy gap, also the local magnetization, the Edward-Anderson order parameter, and the instability towards the spin glass phase. And it gives you a consistent picture of dimer phase to QSG phase transition. There are some outlooks. For example, we are actually supplementing this whole thing with a analytical method. We have some preliminary result on that. And we have to also focus on finding out whether there is a intermediate phase that comes into the picture from dimer to quantum spin glass, if there is an intermediate phase. So these two are the things that we are trying to do. Yeah, so that's it. Thank you.
Thank you.
Yeah.
Actually, I have a question which is like useful in terms of circuit implementation of this. So, like the calculation that you took is just between 1, 1
Yeah.
Just I wanted to ask, like, will the physics change a lot if we are again taking all-to-all couplings, all-to-all interactions in both the coupled models?
Yeah, because then, I mean, you cannot see that there is a, I mean, all-to-all couple that you would propose, they would not form a singlet, right, between the pairs. So the dimer phase is, already gone. So we are tracking a ordered versus disordered phase transition. So I don't think you would get that there. If you,
We would still get a spin class type.
yeah, there has been studies on that. I mean, coupling between those two balls, let's say SOI balls. There's been studies on that. I'm not very, I cannot comment on that right now. Yeah, anyway.
Any other questions?
Yeah.
So let's thank
Yeah.
speaker again.
Thank you.
Very good evening to all of you, and thanks for staying so late in the evening also. So I'll be talking about novel critical state with G2 gauge fields, and this work has been done in collaboration with Hiranmay, who is a student with Professor Vijay Sinha at IIC, and my PhD supervisor Soumya Bera. So, and this work has been published in Physical Review Letter, and this is the reference. Okay. So let me start by saying what we mean by a G2 gauge field. Okay. So we start with Hamiltonians like this, which have hopping Tij, and that can take only two values plus minus 1. Okay. So these are the G2 values that we are discussing, and we will write down this Hamiltonian on a square lattice which is bipartite, and because of that I can write down this Hamiltonian in this block of diagonal form. Okay. And I have taken one particular configuration here which is called a Landau gauge choice, in which these orange bonds are -1 and the blue ones are +1. For this particular gauge choice, if you count the number of negative bonds, you found that there is a pi amount of flux in every placket because there are odd number of negative bonds are there. And you will also notice that this is actually a perfectly periodic system if you consider this 4-side unit cell, and that's what it repeats. So in the Brillouin zone, what you find is that there are two unique Dirac cones that sit in the Brillouin zone, and this is what is typically known as the pi flux model. Okay. Now then, what is the disorder? So the disorder we are considering here is a pi flux defect that you create on the lattice, and that you create by destroying locally the pi flux on this placket. To do that, you have to flip all the bonds to the left of this placket, and that creates this isolated pi flux defect. And then to understand the effect of this defect on the Dirac electron that is sitting at the band center. Now the question is, why are you interested in such a problem? We are interested in such problem because if you consider the K-type honeycomb model, which is this coupling constant Jx, Jy, Jz, and typically defined on a honeycomb lattice like this. And in the Majorana representation, if you look at the Hamiltonian, it's actually free fermionic Hamiltonian with couplings Uyj, which takes these G2 values. Okay. Now, if you look at the ground state of this Hamiltonian, it's actually considered to a case in which the product of all these gauge fields in all these plackets becomes 1. Okay. So that is your ground sector. And then if you want to understand the excitation spectrum of this Hamiltonian, all you need to do is to flip this Uij bond and destroy these fluxes locally in each placket. And in our model, that's what we intend to understand. Now, what is the symmetry of this problem? Now, in symmetry wise, if you look at it, belongs to this BDI class of problem with this particular signs for time reversal charge conjugation and sublattice operator. Okay. And to understand this, let me just introduce you to what is called a multifractal analysis, in which you look at the different moments of the wave function and look at how they scale with system size. That exponent is called tau q. If you have an insulator, the tau q actually 0, you have an insulator and the PQ will not flow with system size, whereas if you have a metal, the tau q actually linear in q. For a critical point, what you found is that the tau q actually a non-trivial function of q, and given by this dq, which is called the fractal dimensions. So that means if you have a critical point, that can be of many different types. The first one is called a non-singular tau q, which is linear and then it goes up. It can also be a termination kind, in which the system scales like a metal in the beginning like linear q, but then it saturates. or it can show something called much more dramatic, which is called freezing, in which it first increases like a metal, but then it becomes an insulator, like it becomes tau q becomes 0, and it's called the freezing. Okay. So in BDI, the problem, the symmetry class we are discussing, a lot of studies has been done, and what people have found is that, for example, with graphene with vacancies, they found that this tau q shows this freezing behavior, that it goes and becomes 0 later after a certain higher moments q. So what is this freezing is that the wave functions become very highly fluctuating in the lattice, and because of this, the IPR, the P2 for example does not scale, it behaves like a insulator. But if you calculate the conductivity, it does not go to 0 like an insulator, but it's a finite number. So it's a critical metal defined by this finite conductivity, but its IPR don't scale. Okay. Now let me convince in the few minutes that the problem of a pi flux is much more richer than the graphene vacancy problem I discussed. So when you talk about this G2 flux excitations, you can have a single monopole defect, a dipole, a tilted dipole, a quadrupole, or a Greek cross defect. And we need to consider all such excitations, because if you look at the many body energy and look at the lowest energy excitation, a dipole is actually having a lower energy compared to a single defect. So at a low enough temperature, this is the fast excitation that you encounter in the system. So studying all these things gives us this energetic hierarchy of states, and to understand all these states properties. So what we calculated is called a localization length divided by the system size using transfer matrix. And what I am plotting here is that as you create a concentration of this defect, either the single or the monopole or dipole, each of them individually at certain concentration, and you look at a system size higher and higher, what you see is that all these systems go to a limiting value of m by j, which you can extract from the final value from this one. And that's what I am calling this j, and this is what is plotted inside this as a function of concentration for all these kind of defects. So the message is that all these kind of defects with their local correlation finally go to a critical state, which can be labeled by this small j values. What about the conductivity? The conductivity for all of these defects also create a zoo of critical state, which are labeled by their conductivity values as such. If this dotted line is actually the graphene is the conductivity of the clean Dirac cone, and if you put disorder, the conductivity actually increases, and you have this zoo of critical state depending on the local correlation between different kind of defect configurations. Now what about the multifractality that I talked? If you calculate the multifractality for this pi flux defect problem, what you found is that it shows freezing behavior. It does not show freezing, but it shows termination behavior. And we ensure that by taking a derivative of this slope and showing that it terminates rather than a freezing that you see in the graphene that I discussed. And then the question is then how do you understand this termination behavior in this case? So we wrote down a low energy field theory, and the field theory has this random gauge and random mass terms, and their variances are this coupling constant. And if you go and write down the flow equation, this is how the flow equation looked like. The mass coupling flows to 0, but the gauge coupling actually increases if you have a finite gauge coupling, a finite mass coupling term. What this means is that people have shown is that if this gauge coupling, a gauge variance term grows more than certain limiting value, what we found is freezing. But for our case, we found that this mass-mass correlation not equal to 0, so you expect a freezing like behavior like after a certain scale, but we don't observe that. And we found out that the reason for that comes from the fact that these defects are not uncorrelated, they have local correlation between them. And when we included this correlation among them, and now this is this coupling captured by this coupling constant between the gauge and mass term, we found this new set of flow equations. What this tells you that for any generic value of, if you start with certain values of this coupling constant, all your coupling constant decreases at the largest system size. But if you slightly detune each other and start with different value of initial condition for all of them, what you find for the initial few length scales, this coupling constant decreases, so it try to avoid freezing, but ultimately as the largest system size it again increases, so freezing will inevitably happen, but it will come at a very large system size which numerically can never be observed. Okay. But to our most surprising, what we found is that there is a universal relationship that holds between all these kind of defects with their local correlations. So if you plot the conductivity of the system versus this limiting value of the localization length value, and all of these defects with their different kind of local correlations fall on this universal line that they obey. And this shows that the crucial properties of the BDI with their critical nature, and this is a very the universal line shows that irrespective of the local correlation, you can never avoid this line that you ultimately be able to reach. So this is the conclusion that there is a universal description that you can have irrespective of any local correlation. Ultimately, this is the line where you will stay, and this description is independent of the local correlation of defects between the plaquettes. With this, I would like to thank you, and any questions, please.
It was not very clear when you went to the continuum. So because in the discrete case you only had plus minus pi, right?
Yeah.
So in the continuum that condition is relaxed.
You mean in writing this field theory?
Yeah.
Oh yeah, so this is a disordered Dirac field theory. So you start with the Dirac Hamiltonian, and then write down terms allowed by the BDI symmetry, and then do a coarse graining to go to this continuum Hamiltonian, and then we do some supersymmetric analysis to write down this flow equations.
You can discuss I didn't understand. Any other questions? If not, yeah, let's thank Naba and all other speakers in this section. Thank you.